Okay, guys, so welcome to the next lecture. This is where things start to get real in physics, as the kids say. We're going to start talking about two-dimensional kinematics. What you've done up to this point have been one-dimensional. Things like throwing a ball straight in the air. And you only have to worry about the X or the Y axis at any given time. Those are very good introductory programs, but they don't really represent the real world too well. Most of the things that we need to deal with in the real world are 2 or 3 dimensional. In this class, we're going to limit ourselves to just 2 dimensions. We're not going to worry about a Z dimension too much. And we're certainly not going to worry about 4-dimensional things where we have to talk about time. We're just going to talk about X and Y. But that introduces its own set of interesting problems. Predominantly, this is going to use the trigonometry stuff from the last lecture. My plan here is to go through the slides, or at least most of them in this lecture, to give you a general idea of what's going on. And in the next lecture, I plan on predominantly just working problems and examples, so you guys can see how this is done and give you some tips on how to work the problems. So this is an example here, this roller coaster, of something that would be 2 or 3-dimensional kinematics. If we go back to our example of throw the baseball in the air, we can see very easily that we can just kind of calculate the time it takes to go to the top of the arc, come back down. We're only worried about Y. In the case of the roller coaster, if we wanted to measure the position of this car, its velocity, maybe its momentum or something, at any given time, you can see how that gets kind of tricky, right? Because it depends on where we are on the track. It depends if we're in this loop, if we're in this bank or something. And notice that the loops and the banks are not squares. They're not complete vertical. They're not complete horizontal. There's some tilt. There's some angle. So that's what we need our 2-dimensional kinematics to work. This is more of an example of a 2-dimensional kinematics problem, or a 1-dimensional really, or a combination of 1-dimensional. So New York City happens to be laid out in a grid. So this is just kind of an above ground view, or above buildings view of New York City. And you can see that the streets are laid out nice and straight. So it's really, really easy to say, okay, I'm going to go, north on this street and west on this street. And you don't really have to do a whole lot of kind of northwest kind of calculations. This is kind of what it looks like. Now, if we wanted to describe our position in New York, we can use this instead of doing 2 separate 1-dimensional problems. We can just make a single 2-dimensional problem. So we can see here, notice that we have done something a little different with our coordinate system. You're kind of used to putting your origin in the bottom left corner. In this case, we've put our starting point for east-west in the bottom left corner, but we put our starting point for north-south in the bottom right corner. That's okay. Remember, we can do whatever we want to do with our coordinate system to make the problem easier. In this case, this happens to be a convenient representation of what we're trying to do. So if we want to describe our destination in this case, notice it's marked for us a destination up here. It's not enough to say that we are 5 blocks away from our starting point, because we don't know what direction we're talking about. It's not enough to say that we're 5 blocks away to the north, because that's not sufficient. If we talk about our starting point, 5 blocks to the north would be up here somewhere. So what we have to do is say that we exist at some combination of the 2 points. In this case, We're 9 blocks to the east and 5 blocks to the north. Conveniently, if you imagine a line going from the starting point 0 straight to the destination point, that makes a nice right triangle. So if we wanted to find, in this case, total distance traveled, we would simply add our 9 plus 5, which gives 14 blocks. But our displacement is not going to be 14 blocks. Our displacement is going to be whatever the hypotenuse of that triangle works out to be. You know that the x value is 9, the y value is 5. So 9 squared plus 5 squared, let's see, that's 81 plus 25, 106 square root, whatever square root 106 is. So that's going to give you whatever your displacement happens to be. It has to be the longest side of the triangle, so it's got to be longer than 9. I think root 106 has got to be something like 9.5, 9.8. I don't know what the math is off the top of my head, but you can see that that's going to be a pretty good estimate. This is two-dimensional kinematics. If we want to know the position of a particle in an X and Y plane instead of just an X or just a Y. This is what I was talking about. If you want to calculate that displacement, then we imagine a right triangle with sides A, B, and C. Pythagorean theorem tells us all we need to know there. I want to point out something else in this slide. Notice that we've drawn our starting point with a direction. So this is a vector because it has magnitude and direction. So we've drawn our starting point as an arrow facing to the east, and then we've added our north direction as another purple arrow pointing to the north. But notice how we arranged them. We added what's called the tail of the vector. The head of the vector is part with the arrow. The tail is part without the arrow. So we've put these vectors together, head to tail. Whenever you add vectors, this is how you do it. The resultant vector is what you're going to get, is going to effectively be this hypotenuse. In this example, notice that we're talking about distances. And our units are in blocks. They're not necessarily meters or feet or miles or anything. We've just got some arbitrary unit called a block. I don't remember what the size of a block in New York City is, maybe a quarter mile or something. If you care, go get into civil engineering class. They teach all that kind of stuff. But if you take away the units of blocks, and I take away east and north, if I just call it the positive X direction and the positive Y direction, and instead of blocks, I call that velocity or acceleration or displacement or whatever I want, notice that the map does not change. The way the vector behaves does not change. So it doesn't matter if I'm talking about distance or velocity or whatever, all these rules are going to be the same. So don't get confused and scared when you go to do the homework and you find that we start talking about velocities in the X or velocities in the Y. That's okay. It's still just a right triangle problem. As long as you're using the same units for everything, you're fine. Now, something to be aware of when you do those kind of problems, though, you might see something that says, if we're talking about velocities, you might see an X direction velocity given in meters per second, and you might see a Y direction velocity given in miles per hour. Well, those two units are not the same, so you're going to have to convert meters per second to miles per hour to meters per second, whatever's convenient for you. So just be careful of that. But once you get your units all together, it becomes just a pretty standard right triangle problem. So here's the same problem illustrating this displacement concept. So now instead of having to drive my car and presumably stay on the roads, I get a little pissed off in New York City if you don't drive on the roads. If we're confined to the roads, we have to do this kind of 9 blocks east, 5 blocks north. But if we're not, if we're in a helicopter, we can fly that straight line distance. And it works out. Look, I was pretty close. That my distance is about 10.3 blocks. But notice I have this angle, this 29.1 degrees. If you remember from our brief discussion and review of trigonometry, we can use those trig functions of sine, cosine, and tangent to find what that angle is. In this case, we know all 3 sides of the triangle. So we could certainly use any of those functions we like to get that angle. And you decide. So let's say that just for convenience, I'm going to use if I want that angle right there, that's marked as 29 degrees. This symbol right here is called theta. If I talk about an angle theta, that's what I mean. That's the Greek letter we generally use to represent angles. So if I want to find this angle, well, let's see. If I use the opposite side of this angle, that would be that 5 blocks. And if I use the adjacent side of the angle, that's 9 blocks. So if we go back and we think, okay, which trig function uses opposite and adjacent? What is it? Remember SOHCAHTOA. Tangent is opposite and adjacent, TOA. So we say tan theta equals opposite over adjacent. So the opposite side in this case would be 5, the adjacent side is 9, so 5 divided by 9 gives you tan theta. Take the inverse of 5 divided by 9, and you should come out with 29.1 degrees. If you don't, you're putting this in your calculator, and if you don't, and you come out with something like 0.08 or something, remember you're in radian mode, and you need to go to degree mode. If you didn't like tangent, if you wanted to use sine, so that sine is opposite over hypotenuse, so the opposite side would be 5, hypotenuse is 10.3, same kind of calculation, except you take the inverse sine, you get your theta, you still come out with 29.1. This is going to be useful. Again, think of these things as vectors. What if these are velocities? And let's say that I give you a velocity that the helicopter is flying at. So if I gave you that it was flying at 10.3 blocks per hour, or whatever it is, right? Or even if I just wanted to use the units here, if I said helicopter travels 10.3 blocks from the starting point to the destination, and it makes an angle of 29.1 degrees with the horizontal, and then our horizontal component of the travel is 9 blocks, find the north-south block unit of that. Again, just a trig function. In that case, we would know the hypotenuse, and we would know the adjacent angle. So the cosine gives you adjacent hypotenuse. Plug that into your formula, solve for the other side, and you work out your 5 blocks. So this is really useful. What we're going to see here probably next week is we're going to start looking at, let's say I push a block up a hill. Let's say we have this same diagram, but now I have a box on this hill, and I want to know how much gravity affects that box. Well, it certainly depends on the angle of the ramp. So this is going to go into, when we start talking about energy in a few weeks, talking about work and energy. This is why when you load a U-Haul truck, for example, they give you a ramp instead of just letting you pick the box up and put it straight into the truck, because that's hard. So if you have a ramp, it's easier to walk up the ramp over a distance, and that's a function of that angle. And we're going to see how to do those calculations. So same kind of idea here, except we have a particle. And in the first example, let's say that our particle moves to the right, but gravity is pulling on it. So we can see that our green vector, which would represent gravity, is kind of constant, right? And then because we moved from left to right, we have a position vector that moves to the right. The more time that passes, the bigger those velocity vectors get, obviously. So if we dropped a brick off a building, after 1 second, it's not going very fast. After 10 or 20 seconds, it's going pretty damn fast. So that's going to accelerate. That's your compounded square function. Let's see, that's just talking about displacement in a different way. So this is what I was just talking about, using distance measurements and angles. You can find any other side of the triangle that you want. Extraordinarily useful. It's a couple of different examples of that. So in the first case, if we have a displacement of 25 meters along the hypotenuse, and we know the angle between the hypotenuse and the horizontal axis of 49 degrees, we can use some trig to find out what that horizontal axis would be, right? Because we know an angle and we know a side. As long as we know an angle and one side, we can find another side. If we know two sides, we can find an angle. Remember algebra 1. If you have an equation with 3 variables, in this case, we have, for the trig functions, we have an angle and 2 sides. So that's an equation with 3 variables. As long as you know 2 of them, you can solve for the other one. The same thing works here. If you know an angle and you know a side, you can find another side. If you know 2 sides, you can find an angle. That's all we're going to be doing. And you can see that the expression to calculate that first graph at 49 degrees looks very similar to the expression to calculate at 15 degrees. Obviously, your distances are going to change a little bit because you've got different measurements, but the procedure is the same. The last one looks a little different, but it's not that big a deal. All we're doing here is changing a sign. We're used to thinking about those first 2 cases. We're used to thinking about that as the positive direction. Well, in this case, we have an angle and we have a side. But if we calculate the length of that x direction, that's certainly going to be positive. But if we calculate the length in the y direction, that's going to be negative. So how do I know that? Because that's how I chose the coordinate system. I know that up is positive in this case, positive y, and to the right is positive x. Well, this thing is still generally pointing to the right as far as the x coordinate, so that's going to be positive. But it's generally pointing down in the y coordinate, so that has to be negative. So remember that when you plug your numbers into the equations, keep in mind angles. Another way you could do that, if you didn't particularly know which direction was positive and negative, or you have a brain fart and you forget, there's nothing wrong with saying that angle is negative 68 degrees. Right? If I made a 68-degree angle pointing up and to the right, that would look exactly like a 68-degree angle pointing down to the right. They would both measure 68 degrees, but we have to have a way to distinguish which one of them is on which side of that axis. So we can absolutely just put in a negative value and work the equations. No matter where we put our negative value, we're going to get a negative value out somewhere on one of the sides or the angle, and that tells you how everything's oriented. Remember, in physics, the sign, the negative sign or the positive sign, just tells you direction. That's all we're doing. So many students get wound up in what direction is positive and which one is negative. The short answer is whichever one you feel like making the positive. Whichever one makes your life easier, just make sure you're consistent on the whole problem. So in this case, let's say we have these three vectors, these A, B, C, and we want to find the resultant vector. Let's say these are distances and we want to find the displacement. Well, we could certainly do this as three separate problems. We could certainly look at, if we made three different triangles, we made a triangle here, a triangle here, and a triangle here, we could certainly calculate the different displacements. Add them all together, take an average, and we could get there, right? That's gross. That's tedious. You can see how tedious it would be just with these three vectors. So the other thing we can do is just take an average. We start at the beginning. We draw a vector all the way to the end. If we know that angle, we can calculate this side, right? And that's all we've done here. If we were to measure, if we were to draw this, and we measured and said, that vector is 50.8 meters. And then I took a protractor and I measured, that's 5.47 degrees. I know a side and I know an angle. I can find the X or Y position. In this case, our Y position is probably going to be negative because I've probably chosen positive Y to be up. So our Y position is probably negative, not a big deal. If these were velocities instead of positions, what would that look like? If this was, say, a cannonball, it would look like the cannonball is moving to the right, but gravity is pulling it down. So this eventually looks like an arc. Well, you might look at this and go, how the hell does that look like an arc? Imagine if we took a whole bunch of these little vectors. Imagine the path of the cannonball. But instead of measuring in terms of meters, we take a distance measurement at the millimeter level or the nanometer level. It's going to be a shitload of triangles. It's going to be a whole lot of work, right? But if you start adding all those really, really small triangles together, instead of getting this kind of jagged, kind of up here and then sharp turn and then sharp turn, that would start to get more and more smooth, right? And so that's where your arc comes from. It just so happens, non-testable information, but I want you to know this. This is how we would use calculus to solve this problem. In calculus, we have a thing called the integral. The integral gives you the area under a curve. And so if we happen to know what that arc looked like, if we could define the equation for that arc, we could simply integrate that arc over time and get the same value here, instead of having to do this with a bunch of small triangles. And instead of having to do this, with small triangles and get a rough estimate and take 3 or 4 iterations of triangle problem. If we use calculus to do it, we can do it one step. Which is why I really, really love calculus for doing physics problems. Coincidentally, if you didn't know, calculus was invented because of physics. Isaac Newton was attempting to describe the world around him. He was attempting to describe the motion of objects and gravity and things like that. And he decided that algebra was not sufficient for the task. So he had to invent a new mathematical system to describe things in kind of shorthand, and that's calculus. Wrote a book called Principia Mathematica. You can get it in the university library. If you really are into pain, you'll read it because there's a lot of theoretical mathematics. Anyway, notice that this is just another way to express our positive and negative. So the negative of a vector is just another vector with the same magnitude, but it points in the opposite direction. So in this case, if we have some vector B, it's pointing to the top right. The opposite of that would be pointing in the opposite direction, so it's got to be bottom left. But notice they're the same length, same magnitude. That's all we're doing. Remember, signs just mean direction. Some more examples of the same thing. We have an XY coordinate system where Y is positive in the up direction, X is positive to the right. We define a couple of scenarios. One, we have an angle of 66 degrees. The other one, we have an angle of 112, but pointing to the opposite side. I would probably do this problem by saying that's an angle of negative 112. And you'd still get the same answer. Just remember, you got to have a negative in there somewhere, depending on what coordinate system you're using. No big deal. Remember, if you have a straight line bisected by something, this is basic geometry from 10th grade, that the sum of those angles is 180. So we could work the problem that way as well. Not a big deal. So what happens if we have to add vectors? Or if we have to, more often than not, it's really, really difficult to describe the motion of an object using just that, what we call the resultant vector, that kind of diagonal line. So we have this idea, this concept that we're really going to dig into, and you're going to hear me use these terms a lot. We have in this case, the resultant vector is the result of the addition of this vector on the bottom, we're going to call a sub x, and the vector on the right that points up called a sub y. These are called component vectors. So if we have some vector capital A here, that's our diagonal line, it is made up of an x part and a y part. In this case, a sub x is the x part, a sub y is the y part. So you can see the equation that says a sub x plus a sub y is a. That's the total vector. Here's something that I think you might not have thought of up to this point. It did not occur to me until well into my undergraduate studies, but it suddenly made trig make a whole hell of a lot more sense. Let's say that we have this diagram. We have this vector A, and I know, just kind of intuitively looking at this, that it's got an X part and a Y part. Well, how much of it is X and how much of it is Y? That depends on how big theta is, right? That depends on what that angle looks like. So if the angle is very small, in other words, closer to aligned with the X plane, then your X contribution is going to be bigger. If the angle gets larger, then your Y contribution is going to get bigger and the X contribution is going to get smaller. So in very general terms, without putting numbers to it, we can say, well, if we have a vector A, how much of it is the X component? And you might say, well, some of it. And then I'll go, okay, good answer. And I'll say, well, how much is in the Y component? Well, the answer is the rest of it. So what we need is some kind of function that tells us the percentage of the total vector that belongs to the X component and to the Y component. What's a percentage? It's just a ratio, right? It's a certain number of parts out of 100. Or a certain number of parts out of a whole. If our whole is a circle, we divide the circle into chunks that we call degrees. So a certain number of degrees out of 360 gives you that percentage, right? So what are sine, cosine, and tangent of an angle? They simply give you the percentage of the vector that belongs to either the X, Y, or Z component. In most cases, if you orient your coordinate system such that Y is up positive and X is positive to the right, then the total angle time, or the total vector times the cosine of the angle will give you the X component. And the total vector times the sine of that angle will give you the Y component. That's all trig does for you. Trig tells you the percentage of the total vector that belongs to the X or the Y component. So that's a way to mathematically answer how much of vector A is made up of A sub X, some of it. How much? It depends on the angle. Well, what part of the angle? Whatever the cosine function turns out to be, whatever the cosine of that angle is, that's your percentage. Think about, there's a couple of unique angles. If we think about 0 degrees, so imagine this A sub X vector in relation to the X-axis here, that angle would be 0. How much of A sub X in that case is on the X-axis? All of it. The angle is 0. So what's cosine of 0 have to be? It's got to be 1. 100%. 1.00. Taking the same example, we have A sub X lies directly on the X vector. How much of that is on the Y? Well, what's the angle between the X component and the Y component? 90 degrees. What's cosine of 90? 0. What happens if you take a 45-degree angle? That should give you about half, right? Should be about half in the X and half in the Y. So cosine theta and sine theta are both going to be pretty damn close to 0.5. If you don't believe me, go back and look at the unit circle stuff that I covered briefly the other day. But again, that's something that I kind of discovered on my own about halfway through my undergrad studies, that, oh, trig is just telling you the percentage of a vector, just a function of the angle. A lot of people are scared of trig when they first see it, because they're like, oh, what the hell is this degree thing? What the hell is this angle thing? What's a radian? It just seems like these arbitrary values of sine, cosine, tangent. Not really arbitrary. They are a function that tells you a percentage of that angle, or the percentage of that vector. That's a function of the angle. Be careful. Having a sub x be the cosine theta times the whole vector does not always give you the x components. You have to get good at visualizing this. If you were to invert this triangle, or you were to rotate that triangle 90 degrees, you get a little different answer. So this is why you need to think carefully about what is the opposite side of the triangle, what's the hypotenuse of the triangle, what's the adjacent side of the triangle. And then knowing those trig functions will tell you which component you're getting. So here's exactly what I was saying. Given this setup that we have, that we've been looking at, this 29-degree angle between a 9 block distance in the x and a 5 block distance in the y, that works out, gives a hypotenuse of 10.3 blocks. Well, if we want to know how far north our displacement is, we need the y component of the vector. So a sub y is just a times the sine of that angle. Well, we know the total vector a is 10.3. We take 10.3 times the sine of the angle, which is 29.1. Stick those in our little algebraic formula, and we come out with 5 magically. If we want the x component, a sub x is a cosine theta. So we end up with a magic value of 9. Interesting. So we can use the knowledge that a sub x is a cosine theta and a sub y is a sine theta. That gives us the magnitude and direction of a vector. Remember what we said earlier. Our basic definition is this: a sub x plus a sub y is a. If a sub x is a cos theta and a sub y is a sine theta, then that means that a cos theta plus a sine theta is a, right? You could factor out an a there, and you get a times sine theta plus cosine theta equal a is 1. Well, so then divide through by a, and you get cosine theta plus sine theta equals 1. That should seem familiar. That is a trig identity. And that's where it comes from. Very, very useful. So we can use the tangent, right? Same thing. We want to know the magnitude direction of the resultant vector. If we know a sub x and we know a sub y, we know that theta is the inverse tangent of the ratio of y to x. So theta equals inverse tangent a sub y divided by a sub x. That gives me an angle. And if I want to know what the magnitude of the vector is, you just use Pythagoras. A equals root x squared plus ay squared. Pay attention to notation. This is a sub x squared plus a sub y squared, not a times x squared and a times y squared. It's real easy if you're not careful writing this down and how you annotate this. It's really, really easy to misplace a square or an x or y. Different kind of notation, same example. Some vector A and some vector B. Remember, you line up head to tail. with your vectors, and then you draw the rest of your triangle. And that gives you your resultant vector. So your vector A plus vector B gives you the resultant vector R. Well, cool. What if we wanted to know something about those angles? If you look at both component vectors, vector A and vector B, you can break each of those down into an X component and a Y component. So we have an A sub X, A sub Y, we have a B sub X, and a B sub Y. Notice when we do that, look what we've done. We made nice little right triangles that are very easy to solve, as opposed to this nastiness, right? So if you wanted to know what that resultant vector R was in terms of A and B, well, we know that R is A plus B, but we also know that A is A sub X plus A sub Y, and we know that B is B sub X plus B sub Y. So you can make those substitution and just enjoy banging your head against the wall for the next hour doing tedious algebra. Again, calculus makes this way, way easier. Unfortunately, this is an algebra-based class. But if you really care and you want to stop by my office someday, I'll show you the calculus. A whole lot easier. So this just shows you, just digs a little into the calculations there, which I will leave for you on your own. So here's where I want to go with this. So here we have somebody that's kicked a soccer ball, footballs and saying, you know, and we have some displacement S. Notice that's that resultant vector S. We know that it has components X and Y on the horizontal and vertical axes. We know it's the magnitude of S, and it makes some angle theta with the horizon. So some of the things I might want to know. How high did the soccer ball go when I kicked it? That's the Y component. How far did it go in the X direction? That's the X component. Well, if I know the angle, I can find those. And these are the kind of examples I'm going to show you next time. If you were to pick points along that arc, notice that we can break that vector down, that resultant arc, into as many small right triangle problems as we want. So that's all this is doing. So we're just taking an arbitrary point and we're saying, okay, where is this thing? Where is its A position? Where is its X position? Where is its Y position? We can take as many of those as we want, add them all together, and we end up with this nice little arc. Notice, in this case, no matter where we are on the arc, X and Y do not change direction. X is always positive, right? Y is always positive up. The only thing that's changing is the angle and the magnitude between the two vectors. That's all we're doing. I think this is where I'm going to stop for today, because I think I want to work some problems like this for you the next time. I'll just use the whiteboard here in the class, and I'm going to show you how to calculate some of these problems. And we'll probably start with this problem, this fireworks show. Now, all these notes are already posted on Blackboard. And as always, I will post the video for this probably later tonight. But I encourage you between now and the next lecture on Monday, presuming that we don't have another giant ice storm, go try to work this out. See what you can come up with. Remember, it's just a right triangle problem. That's all we're doing. Don't let it scare you. Anybody have any questions, concerns, smart-ass remarks before we're done today? Nope. Okay, then I will see you guys next lecture.